Hey, everybody. So I'm going to go through the third PowerPoint. Now, by this point in the semester, most of this stuff will be repetition for things we've already talked about. So this is a really easy lecture. You can take some notes on it if needed. This should already be in your notes, at least most of it. So you might have just a couple of things to jot down, but it's a good review prior to taking the test because a lot of this stuff will be covered on the test, but I think it's pretty straightforward and easy. So I'm going to PowerPoint 3, Thunderstorm varieties, and this, oh, I should probably share my screen. That would help. So here's the thunderstorm ingredients. We need a source of lift, we need moisture, and we need instability. So once again, just reminder, lift, moisture, instability. That's always what three ingredients we need for thunderstorms. Now, lift is a dynamic process, meaning I'm lifting the air. In class, I always said, I lift the box. But in the atmosphere, the air is forced to go up. It's forced to ascend. It has to do that. So you might have a front, like a cold front or a warm front, or maybe a dry line, a sea breeze circulation, orography, meaning mountains, topography. So if it's going uphill, maybe an outflow boundary from a previous thunderstorm or even an ongoing thunderstorm, but we need something to initially get the air to go up. Now, the second thing we need is moisture. We're going to talk about that in this upcoming unit, but a lot of it is just water vapor. So the dew point's the easiest way for us to look at this. We want high dew points. And then instability, which we've talked a lot about. So that's buoyancy. So we need lift, moisture, instability. Now, how do we know this? If you recall in our discussion, we said when I lift a parcel, it's going to behave a certain way. The pressure is going to go down, the box will expand, and the temperature goes down adiabatically. Originally dry adiabatic, which is 10 degrees Celsius per kilometer. After that, it's wet adiabatic, which is something less than 10. And it's a variable quantity. It depends on how much water vapor is actually condensing. And when water vapor condenses, latent heat is released inside the parcel. We also said that instability is a race to get cold between the environment and the parcel, and we want the environment to win. So that requires knowing what the environment is actually doing. Okay, so I've asked you kind of a smart ass question or given you a smart ass answer. I guess the question's fine. What's the environment doing? And the answer is it can do whatever it wants. So if you're going to know what the environment's doing, you need to measure it. Well, I'm showing you a picture of somebody launching a radio sonde, and in my class, it's kind of become tradition that you know the guy's name. His name is Bob. So what can the environment do? Anything it wants. How do you know what it does? Ask Bob. Okay, so this is Bob. Now, where do you think Bob's from? And the answer is Texas. Look at that belt. Little metal rivets there on the belt. He's got his kind of a foamy cap over there from the National Weather Service. And actually, his real name is Bob. I met him when he was launching a balloon. And this is just the equipment on the ground. This is in the balloon. It's got a little radio control, so that's why it's called a radio sonde or a ray wind sonde, radio wind sonde. It sends the information back to a person who can monitor that on a computer. So if you want to know what's happening, ask Bob. Where's Bob from? Texas. Okay, keep that in mind because I might even ask you that on a test. I think that's kind of funny. We talked about on the way to becoming a thunderstorm. We have the development stage. So within the development stage, we have cumulus, which is fair weather cumulus. It can be congestus or what we call moderate Q, and then a TCU, towering cumulus. Eventually it becomes a cumulonimbus, a CB, means it's precipitating. We are now going into the mature stage as that rain falls. This was a really nasty thunderstorm. It killed a lot of people. Luckily, they were able to get them buried really quickly. Just kidding. Okay, a couple things you want to know is about the texture. So this might be something you need to take notes on. The texture of the cloud, when you are seeing it all cumulus-like or cauliflower-like, where you see all the little features and shadows, we say that that is rock hard. Okay, it looks solid. It's what defines a puffy cumulus cloud. And when it is rock hard, and this is kind of important here, I'm going to bring out my little epic pen so I can kind of highlight a few things. is that it's in the liquid phase. So all the cloud which is visible is liquid water. When the updraft is growing, or if it's a strong updraft that's been there for a while, it exhibits the rock hard texture. So all these little things, rock hard texture, all the way up into the overshooting top. Okay, that's that. Oops, next. Come on, there we go. So here's the rock hard growth. Now, the anvil, which is ice, remember we say that it's a cirrus anvil, and whenever water turns into ice, it loses that rock hard texture and becomes what we know as glaciated. So that would be an icy cloud. Now, the anvil is always glaciated. It's glacial. It is cirrus anvil. But if I go on, I can also see indications of something down here. Now, in this case, keep in mind that it's smoother and softer because there's rain. Rain is not the texture, okay? But if the updraft that we have, instead of being really rock hard, starts to smooth off, we say that the updraft is glaciated, okay? And that usually means it's somewhat weaker. So here's a very strong rock hard tower. You can see the undulations here. But over here, do you see how much softer this tower looks like? This is a much weaker thunderstorm. We were chasing this storm and we thought it was going to be great, and it ended up being a real disappointment. This is a nice solid rock hard tower. So rock hard usually means it's a stronger thunderstorm. Now, the anvil itself, even though it's glaciated, if I take a look here, notice that I'm going from anvil to sky. It's like I could draw a line, like an X-Acto knife, cut it out. That, and I don't even know why it's like this, usually means that this storm is strong. And I just want you to kind of know that. If you ever go storm chasing with me, I'll always be looking for that. So these are, it's very well-defined boundaries of the anvil. And that, in my mind, is just a good sign for a strong thunderstorm. If it's wispy, and let me go back a little bit. If it's wispy, like over here, see how it's not defined? This is a weaker thunderstorm. So a lot of clues that this thunderstorm is not very strong. It's a soft, fuzzy, glaciated tower, and it's not a very well-defined distinction between anvil and not anvil. Okay, now, vertical wind shear increases the longevity and the organization, right? So we've talked about this. We are going to get longer lived thunderstorms because the downdraft doesn't fall through the updraft. It tilts them, it separates them, it allows for air mass thunderstorms to become multi-cell thunderstorms. If there's enough shear, as we're going this way in this diagram, then we get to a lot of shear and we get supercell thunderstorms. And this is something we are discussing in class. I will not have a video on this, but in class, super important that vertical wind shear results in storm scale rotation because it tilts horizontal vorticity into vertical vorticity. This should make sense by watching some of the lectures from the actual virtual classes that we have. Okay, now in this case, if we look at this tower here, we can see that this tower is almost straight up and down, because if vertical wind shear is causing it to tilt, the faster it goes up, the less it's going to tilt over. So over here, this flanking line tower is not the main supercell, and it's tilted. Same environment. This just indicates what? This indicates that we have a strong updraft. A strong updraft means it tilts less. Shear tilts it, it won't be as tilted the faster the air goes up. Okay, so again, notice the rock hard feature of this cloud. Even at the very top, we have the ice cream cone overshooting top. It's rock hard texture. It's still liquid water. This is definitely glaciated on the anvil. Okay, let's see what else we got. Now, sometimes shear is so much that we tilt the storm so badly over, it's hard to maintain inflow into the updraft. So there's times where the CAPE, or the convective available potential energy, which is really the amount of instability, is weak, the shear is too strong. It's not balanced. And we talk about that balance with the Bulk-Richardson number. That's going to be something we discuss quite often. So in that case, sometimes the thunderstorms can't live very long. Most of the times when I talk about this, and I'm just going to reiterate, I want vertical shear, and remember shear is spelled this way, and I want instability. And they're both are relatively strong. It doesn't have to be like super strong, like super high CAPE or total amounts of vertical shear. We want it to be somewhat strong, but the key thing is we'd like it to be balanced. Balanced. And so we have something known as the Bulk-Richardson number, which is the BRN, which is CAPE, the amount of CAPE over the amount of shear. Okay, so this is something to talk about, this balance. The Bulk-Richardson number, it's just a guy's name. His name is Richardson. He was a famous meteorologist in the past. And this just talks about the amount of CAPE over shear. Now, when we put the numbers of CAPE, how many joules per kilogram of CAPE and how much shear there is, and I'm not going to ask you for those numbers. I get a number, and the number we come out, and you can see a computer will tell you what the Bulk-Richardson number is. Between 10 and 45 is called the sweet spot. And when I see Bulk-Richardson numbers, 10 to 45, it's usually the sweet spot. Sweet spot for what? For supercells. That's usually the way these things work. Now, if we have a situation where the CAPE is way more than the shear, then the Bulk-Richardson number becomes bigger. The numerator is big, the denominator is not as big. So the Bulk-Richardson number goes higher than 45, and now we get more like pulse severe storms. We don't get the really good supercell storms. If the shear is too much, like we just see in this picture, and the CAPE is less, then the numbers fall below 10, and then it's hard to maintain a long-lasting thunderstorm. So these are just kind of rules of thumb. It's not guaranteed to be this way, but it is something that meteorologists will often look at. So the sweet spot of the BRN, the Bulk-Richardson number, that's a number you can add, or an acronym, to your acronym list. Okay. Now, when we talk about updrafts and downdrafts, and we are looking at how we determine this, remember that the updraft is a function primarily of how unstable the air. Okay, right over here, how unstable. The more unstable, the stronger the updraft. So if we have weak updrafts, we don't have that much instability. Now, the other thing is when we rotate an updraft, that causes the air to go faster. Oops, I should spell it maybe that way, faster. So updrafts are first how much unstable air there is, how much instability, and then we can have rotation, which makes it even stronger. So if I've got weak updrafts, I probably don't have that much instability, and I probably don't have rotation. Now, downdrafts are a result of the dry air. We talked about where does the rain evaporate? It evaporates outside the cloud. So if I have a weak downdraft, it typically means I don't have that much dry air. It's not causing a lot of evaporation. Now in this picture, and this is kind of irritating to me, is why does this one have a bigger downdraft? The fatter the air, I guess that's what they're implying in the diagram. Why is it stronger? Well, it's something to do with dry air. The dry air could be here, or most likely it's going to be outside the cloud if you get a little bit of shear to cause the rain to fall out. Nonetheless, we tend to think drier air causes stronger downdrafts. So if I have a weak downdraft, weak updraft, this is kind of a lame air mass single cell thunderstorm, nothing too major. Strong downdrafts, this could be what we call a pulse severe storm. It could be just an air mass, but it does have the opportunity to produce microbursts. Okay, so that would be there. Now, if I've got strong updrafts over here, now we're looking at more instability and the potential that these strong updrafts are also supercells. There's enough vertical wind shear to cause rotation. So in both of these cases, we're expecting a strong updraft, and strong updrafts usually have a better chance for larger hail. So the stronger the updraft, the more likely it's severe with large hail. Dry air and high stability, or in high instability, says the likelihood goes up because now we got downbursts as well. And that's again what we're talking about here. If I've got vertical shear, then I know that I might have rotation within the mesocyclone. And as a result, we now say the vertical shear, buoyancy and shear are well balanced. That's the Bulk-Richardson number in the sweet spot. Okay. Now, low bases. This is the last real big thing that we need to talk about for this test. We've already said that the thunderstorm air is with air going up from the ground. We're just going to assume this. So what we're saying is that this box is being lifted and then it reaches the cloud base, and that's the LCL. Now, what determines the cloud base are, well, there's two things you can, it's the same thing, but you can look at it two ways. Okay, and the first one is that the relative humidity is high. Now think about it. The relative humidity is 100% when I'm in the cloud. And it goes up. It stays at 100%. It's saturated. But that means the air is not saturated. So when I lift the box, the air needs to reach saturation. So if it's already high relative humidity, if it's close to 100%, I don't have to go very far before it'll saturate. So low LCLs mean high relative humidity. And that means more moisture in the subcloud layer, the layer beneath the thunderstorm, which means how much rain evaporates, at least underneath it, not much. Okay, so this is a pretty important concept. Now, we look at that with temperature and dew point, the dew point temperature. This is in your glossary. We'll define it in some detail, but we talked about moisture. This difference is called the dew point depression. The dew point depression. And that dew point depression is a measure, it's sort of what we call a proxy, a substitute for what the relative humidity is. The closer these two are together, the higher the relative humidity. So the lower the dew point depression, it's not an acronym, I'm just not writing it out, the higher the relative humidity. Okay? And vice versa. If these two are further apart, the dew point depression is bigger, the difference is bigger, it's a higher dew point depression, and therefore it's a lower humidity. Well, if it's lower humidity, then it's going to have rain that evaporates, which means stronger microbursts and cooler air. Okay, so if I look at storm, here, I'm going to do this. Here's a little picture. Here's storm A. Here's storm B. Let's say everything is the same except how high the LCL is. This is a higher LCL. It has lower dew point, or a bigger dew point depression, a lower relative humidity, more likely to produce microbursts. So B is more likely to produce microbursts than A. Okay? Because the LCL is higher, which means it's drier, which means rain evaporates more. So you have to piece together lots of little pieces of information that I think are pretty straightforward and easy. So this is the one thing you really need to write about. So go back, rewind, get the notes good on this section of this lecture, okay? Then sort of the last information here is that when I have a lower LCL, I have a greater tornado threat. We don't know why. You'll see eventually. Higher LCLs, we don't get as many tornadoes. So when I'm trying to forecast for tornadoes, a lot of times I care about the level, the lifting condensation level. Okay. Now here's a storm. It's a weak storm. Notice it doesn't have very high storm, and the base is very high above the ground. But if it's a thunderstorm, this can still produce lightning. Notice that a lot of the rain is evaporating, so that's Virga. It doesn't have much rain, but there's outflow. It's windy, dry, low relative humidities, and lightning. That creates fire. Okay? So even though we've got these summertime thunderstorms, they don't look very significant. If they're producing lightning and they don't produce a lot of rain, that's when the mountains out west often get forest fire starts. I hope that makes sense. Here's a fairly high base storm. This distance from the ground to the cloud, and you can't tell this, but this is around 10,000 feet. That's very high. High LCLs, it was rotating, but it did not have much chance to produce a tornado. There's a reason for that, which we're not going to get into, but they don't produce tornadoes very much. Storm evolution, we don't have a video of this, that's fine. Thunderstorm types, these things we've already talked about, so just quick review. Single cell, multi-cell, supercell. Multi-cell storms are either clusters or line. And look at this question here, or this question on the test hint. This answer here. The most important distinction is, does a storm have rotation? Because storms that rotate, supercells, are most likely severe. 95% chance they're going to be severe. So the most important question that you need to ask about thunderstorm types is it rotating? If it's rotating, persistent rotation, you have a supercell. If it's not rotating, you don't have a supercell. That's the biggest thing. But overall, single cells, multi-cells, supercells, two types of multi-cells, clusters or lines. Gee, I wonder if this page is important. I'm thinking maybe it is. So this diagram is in the notes. We have talked about this, or we will be talking about it if we haven't done so yet. But if I increase draft strength, which is going to be instability, up, dry air down, and then vertical shear increases the longevity, the lifetime. So when I've got air over here, low intensity, single cell, more shear, maybe multi-cell. When I get toward the middle with more important or more significant up and down drafts, I might get squall lines, multi-cell storms, complexes. They're getting a little bit more nasty at this point. If I have this box over here is a lot of instability, right? Up the axis on instability, the draft strength, but way to the left on shear. So in that case, I get pulse storms, which are going to be severe single cell thunderstorms. That's what a pulse storm is. We'll talk about that in a second. Microbursts. But when we get up here to this side, we have shear and instability, strong and well balanced, and that's where we expect supercells. Now over here, take notes on this, write this down someplace, we'll talk about it. Single cell thunderstorms are, the dominant process is buoyancy. Thunderstorms go up because it's unstable. Multi-cell thunderstorms are dominated by what happens along the gust front. The gust front triggers new thunderstorms if the gust front lifts air to the LFC. We talked about this in class. And then supercell thunderstorms are dominated by, we say dynamic. In other words, it's the mesocyclones, what's going on in the storm. So write that down, we'll reference that later. Single cell thunderstorms are air mass thunderstorms. Notice this one straight up and down. There's not really any shear, doesn't look super strong. They have some lightning, maybe a little bit of small hail. Not usually that dangerous except for lightning. Typically of afternoon summer thunderstorms, we get them. Lightning is your hazard. Everything else is like whatever. They kind of pop up everywhere. Sometimes we call them popcorn, meaning I don't exactly know where they're going to form. They just kind of form anywhere. We're going to look at radar. We're talking about convective initiation. And what we're saying is that the echoes start showing up, the precipitation starts forming up above the ground. But at this point, it's just starting to rain to the ground. So it's going from the development cumulus stage into the mature stage. Okay. Here is a single cell thunderstorm, just sort of basic ideas. Buoyancy is the most important thing. There's no significant vertical wind shear. The cold pool undercuts the updrafts. Lack of vertical shear means that new updrafts will not be generated because we'll see shear helps lift air. Not going on. The whole cycle goes about 30 to 60 minutes. The severe threat is minimal. And even then, it's pretty short-lived, maybe like inch in diameter hail, maybe some gusty winds. Hard to predict that severe weather. You don't give much lead time for your warnings. So, but they're not that big of a threat. And if there's tornadoes, they would be forming in something called a land spout. A pulse severe storm. Now, I'm going to ask you this on a test, and I'm going to ask you to reference this in class. So I'm going to ask you, what are the 4 differences? Oops, let's try to spell this right. Differences between a ordinary thunderstorm and a pulse severe. Now, ordinary thunderstorms, air mass thunderstorms, pulse severe, these strictly are single cell thunderstorms. They form in low shear environments. Make sure you've written that down. Pulse severe storms and ordinary thunderstorms are low shear. A pulse severe storm is because something about it makes it more unstable. Don't know why. Again, this is what we call popcorn severe. Why is this storm going severe? It's like looking at popcorn kernels on the bottom of a pot. Why is that popcorn going to pop? And the answer is, well, I don't know. Must be something, right? So I have a bunch of thunderstorms. Which one is going to go severe? I don't know. One of them does. Why? Well, I don't know. There must be some reason. I don't know what it is. So that's what happens. So when I've got these two, I'm comparing them. Now, the way this is working out is we start the time of 0 when we first start to see precipitation forming in the cloud. So up here, it's cumulus stage, cumulus stage. Once we get to around 10 minutes, it starts to precipitate to the ground. We go cumulus stage, then we go to mature stage, and then maybe after this, it goes dissipating stage. The whole thing, we said 30, 45, 60 minutes, something like that. Now, don't ask me why whoever did this diagram put a cloud on the top and didn't put a cloud here. I don't know. But what are the 4 differences between these two? Well, the first and the most obvious is that ordinary thunderstorms on this one are going up to maybe 35, 40,000 feet. But over here, there are 45, 50,000 feet. So number 1, they're higher tops. If you look at the darker brown as being the higher intensity of the core of the storm, that's what we call reflectivity, but it's basically the radar showing you stuff. Notice how much bigger and more intense this is. That's why it's more likely severe. That's why it's a pulse severe storm. So the core is much larger. Okay, that's 2. Number 3, when does it start raining in an ordinary thunderstorm? About 10 minutes. When does it start raining on a pulse severe? 20 minutes. It takes longer for the precipitation to begin. And as a result, that gives you a little bit of time. If you see this storm going up and it doesn't produce rain as quickly as some of the other ones, well, that's when we start looking at maybe it's severe. Doesn't give you a big lead time, but when I see that larger core and it takes longer to rain, now I'm thinking maybe some severe hail, maybe an inch to an inch and a half diameter hail in a pulse severe storm. A little bit stronger, maybe gustier winds. Not a major threat. It's short-lived threat, but it's still there. Okay? And the last thing is a pulse storm lasts longer. It's bigger, it's gone up higher, it's going to take longer to go away. So those are your four things. Higher tops, more intense core, longer to get precipitation to the ground, and then the storm lasts longer. They're hard to do. This is hard to do for severe weather, but it gives you a few minutes where you might get a warning out before the event happens. A lead time of only a couple of minutes. Oops. Now, I'm gonna skip through this because I'm not gonna ask you about VIL. VIL is vertically integrated liquid. We're gonna get to that when we deal with radar a little bit more. And I just want to look here a little bit on land spouts, because air mass thunderstorms can often do that, because a lot of times land spouts, notice there's not a lot of rain falling, can be in the cumulus stage or early mature. That's usually when you might get a land spout, because you need air to accelerate up. We need the air to be accelerating up. And what that does is it stretches vorticity. But the vorticity is rotating this way. It's already vertical vorticity. It's there. It's not being tilted like a supercell that takes the rotation this way and tilts it up. Your book has some diagrams on that. We're talking about this in class. This one already has something there. So what we say is we get these spouts when there's pre-existing vertical vorticity. And the rapidly forming updraft stretches it and creates a spout. You can do this over land, and it's called a land spout. You can do it over water, and it's called a water spout. Okay, the conservation of angular momentum. Smaller the rotation, the faster it's going to rotate. Helps explain its existence. It is not the whole thunderstorm up here rotating. It's just the rotation here. Okay, so we're stretching vorticity that already exists. And then the question is, well, why does that vorticity exist? Usually it's some boundary. So if there's some boundary, and you will see in meteorology, we care about boundaries all the time. If the winds are different direction at different locations, just even by a little, do you understand that we have horizontal wind shear? Wind from here to there changes, okay? With horizontal wind shear, that means we have vertical vorticity. And the spin already wants to be there. Just like vertical wind shear causes horizontal vorticity, horizontal wind shear causes vertical vorticity. So this is not enough shear to cause that. We don't need shear to do this. We could have no shear at all. But we have a boundary and we have horizontal shear. So when I say there's no shear, there's no vertical shear. And we stretch it into a tornado. And when you see a spout, the spout is usually like an inner core over here. You see the inner core? And then maybe an outer core. But the question is this a tornado? And the answer is yes, because a tornado is violently rotating column of air. Clearly, we have a column of air that's rotating. In contact with the ground, which it's kicking up dust, and the cloud. The mesocyclone is a mid-level circulation within the thunderstorm. We don't have that, but we have circulation, cloud to ground, and therefore it's a tornado. Are these strong? Usually not. I mean, maybe hybrids where there's somewhat of a mesocyclone, but probably not. And when I say strong, we're talking EF0 or EF1 usually. I've seen some spouts at a 2. I'd argue whether it's a 3, but most of the time EF0, EF1. So they're not super high threat, but still EF1, EF2, or EF0, EF1 can do damage. And if it hits some building, it could do some damage to it. So it's still a tornado. You still want a tornado warning. It's just not, your house is a pretty safe place for that. So here's another picture of a couple of spouts. And again, you see that inner core here, that inner core, and then the outer core you can actually kind of see through it. Definitely kicking up dust down here in both cases. It's reaching the cloud base, but there is not a larger storm scale rotation above this in the thunderstorm. So this is an example of a non-supercell tornado. Okay, they're tornadoes, they're spouts. Now we also get them over water. This is over Lake Michigan. They usually form in a boundary, so we have multiple spouts on the same boundary. Remember, the boundary is horizontal. Let's say here's Lake Michigan like this. Here's a map of Lake Michigan. There's a boundary. We are seeing little spin-ups on that boundary across southern Lake Michigan. As we get air that accelerates upward, it's unstable, and we tighten the rotation due to the conservation of angular momentum, and we get spouts. It's over water, so it's a water spout. I think they're cool. I don't know if I've ever seen a water spout, so I'm kind of bummed by that. Oh, and that is it. So let me stop sharing. So the one thing we had in there is this little bit of a build. We'll probably reference that once we start getting into radar, which is next. We're not going to go on to 4 and 5 because we need to use radar to really understand what's going on. This one sort of says, well, let's go catch radar now. So we skipped over 2. We're going to go that as soon as the test is done next week. Okay, so that's your lesson for the day. Make sure if you have any questions, you ask me about them. Hopefully most of it's review, a little bit of stuff about the LCO and the cloud base. That's kind of important. Okay, guys, have a great day.